We have spent the vast majority of our history under the impression that the universe is a static stage, a fixed, unchanging backdrop upon which the drama of existence unfolds. When we look up at the night sky, our senses tell us that the darkness between the stars is merely a container, a silent and empty nothingness. Yet, as our instruments have sharpened, and our perspective has shifted from the terrestrial to the cosmic, we have discovered that our intuition has failed us. We are living inside a phantom. There is a quiet, relentless pressure exerting itself across every inch of the cosmos, a force that does not stem from matter or light, but from the very vacuum itself. This realization challenges the fundamental way we perceive reality. It suggests that the nothingness we have long ignored is, in fact, the most dominant constituent of the universe, dictating the ultimate fate of every star and galaxy in existence. We find ourselves in a peculiar moment in time, where we are aware of a profound cosmic transition but remain unable to grasp its origin. To understand where this hidden energy comes from, and why it is currently pushing the universe apart, we must look beyond the visible and confront the strange properties of the space that surrounds us. It begins with a simple, unsettling observation about the nature of distance. The universe is growing, not in the way a tree grows, adding rings and branches over time. Not in the way a city expands outward, filling empty land with new structures. The universe grows in a way that defies our most basic intuitions about how reality should behave. It grows by making more of itself. More space, more distance, more of the invisible fabric that holds everything apart. This is not a new idea. For nearly a century, we have known that galaxies are moving away from us. Edwin Hubble discovered this in the 1920s, observing that the light from distant galaxies was stretched toward the red end of the spectrum. The farther away a galaxy sat, the faster it seemed to recede. At first, this appeared to be motion in the ordinary sense, objects flying apart like debris from an explosion. But the mathematics told a different story. The galaxies were not racing through space. Space itself was expanding between them. Imagine a balloon with dots drawn on its surface. As you inflate the balloon, the dots move apart, not because they are sliding across the rubber, but because the rubber itself is stretching. The dots remain stationary relative to the surface they sit on, yet the distance between them grows. This is closer to what happens in the universe. Galaxies are embedded in the fabric of spacetime, and as that fabric expands, the galaxies drift apart without ever moving through it. This distinction is not merely poetic, it is fundamental. When we say space is expanding, we mean that the metric of the universe is changing. The metric is the mathematical description of distances and intervals in spacetime. It tells us how much space lies between 2 points, how much time elapses between 2 events. In a static universe, this metric would be fixed. A light year would always be a light year. But our universe does not obey this simplicity. The metric stretches. A light year emitted billions of years ago now spans more than a light year of space by the time it reaches us. This expansion is not uniform in a local sense. Gravity binds matter together on small scales. Planets do not drift away from their stars. Stars remain locked in their galaxies. Even galaxies within clusters hold together under their mutual gravitational pull. The expansion becomes measurable only across vast distances, where gravity's grip weakens and the stretching of space dominates. On these scales, the universe reveals its true nature, not as a container, but as a participant. Space is not passive. It does not simply hold things. It acts. To understand this, we must abandon the classical idea of a vacuum. For centuries, empty space was thought to be nothing in absence, a void. A placeholder where matter could exist but which had no substance of its own. Quantum mechanics and general relativity shattered this illusion. They revealed that space seethes with activity. Virtual particles flicker in and out of existence. Fields ripple through every cubic centimeter. Even in the absence of matter, even in the darkest, coldest, most remote regions of the cosmos, space has properties. It has energy. It has structure. It is something. This realization carries profound implications. If space is not nothing, then creating more space means creating more of this something. As the universe expands, as new distance emerges between galaxies, the total quantity of space increases. And if space itself carries energy and energy inherent to its very existence, then the expansion does not dilute this energy. It multiplies it. Consider an analogy. Imagine a substance that, when you stretch it, does not thin out, but instead generates more of itself to fill the new volume. The more you pull, the more material appears. This would violate our everyday experience with rubber bands and dough. But it captures the strange behavior of expanding space. The universe does not stretch existing space thinner and thinner. It creates new space. And this new space carries with it the same properties as the old space. This leads to a feedback loop, unlike anything else in nature. As space expands, more space comes into being. As more space comes into being, more of whatever energy or pressure is embedded in space comes into being as well. This energy does not arrive from outside the universe, does not flow in from some external reservoir. It simply appears, woven into the new fabric of spacetime as it unfolds. The implications are staggering. In most physical systems, growth requires fuel. A fire consumes wood. An engine burns gasoline. A star fuses hydrogen. But the expansion of space seems to fuel itself. The more space there is, the more expansion occurs. The more expansion occurs, the more space there is. This is not perpetual motion in the classical sense. No laws of thermodynamics are violated within the universe as a closed system. But it is deeply strange. It suggests that the vacuum, the very ground state of reality, is not inert, but generative. This strangeness becomes even more pronounced when we consider the rate of expansion. The universe is not expanding at a constant speed. It is accelerating. Distant galaxies are not just moving away, they are moving away faster and faster. This acceleration was discovered in the late 1990s through observations of distant supernova. And it earned its discoverers the Nobel Prize. It also posed a new mystery. If expansion were simply the aftermath of an initial push, the momentum left over from the Big Bang, we would expect it to slow down over time, dragged back by the gravitational pull of all the matter in the universe. Instead, it is speeding up. Something is driving this acceleration. Something is pushing space apart with increasing vigor. Physicists have given this something a name: dark energy. The name is a placeholder, an admission of ignorance. We do not know what dark energy is. We do not know where it comes from. We do not even know if it is a substance, a field, a property of space, or something else entirely. What we know is that it exists and that it dominates the energy budget of the universe. Dark energy makes up roughly 68% of everything. Matter, both the ordinary matter of stars and planets and the invisible dark matter that binds galaxies, accounts for the rest. This means that the majority of the universe is not made of things we can touch or see or even detect indirectly through their gravitational influence. It is made of something that reveals itself only through its effect on the expansion of space itself. To grasp the scale of this, consider the history of cosmology. For most of human thought, the universe was assumed to be static and eternal. Then came the discovery of expansion, and with it, the realization that the universe had a beginning, a moment when space and time themselves came into existence. This was revolutionary. But even in those early decades of modern cosmology, physicists assumed the expansion would eventually slow. Gravity, they believed, would win in the end. The universe might expand forever, but at a decelerating rate, asymptotically approaching some final configuration. The discovery of accelerated expansion overturned this expectation entirely. Gravity is not winning. Something else is. The simplest explanation for dark energy is that it is a property of space itself, baseline energy density that exists everywhere, at all times, independent of what matter or radiation might be present. This is often called the cosmological constant, a term Einstein himself introduced and later abandoned. In this model, every cubic meter of space carries a fixed amount of energy. As space expands and more cubic meters come into being, the total dark energy in the universe increases proportionally. This is the feedback loop made explicit. The expansion creates more space. More space means more dark energy. More dark energy drives more expansion. This concept strains our intuition because it violates the principle of energy conservation as we typically understand it. In everyday life, energy is neither created nor destroyed. It transforms from one form to another, kinetic to thermal, chemical to electrical, but the total remains constant. Yet in an expanding universe governed by general relativity, this principle does not hold in the same way. The universe is not a closed box with fixed boundaries. It is a dynamic, evolving geometry. Energy can be added to the system as space itself grows. To see why this does not violate the laws of physics, we must return to general relativity. Einstein's equations describe how matter and energy curve spacetime, and how the curvature of spacetime tells matter and energy how to move. In these equations, energy and momentum are conserved locally within any small region of spacetime. The usual rules apply, but globally, across the entire universe, there is no requirement for total energy to remain constant. The expansion of space can change the energy content of the universe as a whole. This has a strange consequence. As the universe expands, the energy density of ordinary matter and radiation decreases. Spread the same amount of stuff across a larger volume, and the density drops. But if dark energy is a property of space itself, its density does not drop. It remains constant. A cubic meter of space today contains the same dark energy as a cubic meter of space a billion years ago, or a billion years hence. The total amount of dark energy, however, increases because there are more cubic meters. This asymmetry drives the acceleration. In the early universe, when space was denser and matter was more tightly packed, gravity dominated. The mutual attraction of galaxies and clusters slowed the expansion, though never enough to reverse it. But as time passed and space grew, the density of matter thinned while the density of dark energy stayed the same. Eventually, dark energy became the dominant force. The more space expanded, the more dark energy there was to push it further. The acceleration began, and it has continued ever since. What does this mean for the fabric of reality? It means that space is not a neutral stage. It is an actor. It does not merely accommodate the objects within it. It exerts influence. It has preferences encoded into its structure, a tendency to expand, a resistance to contraction, a built-in pressure that becomes stronger the more of it exists. This pressure is unlike anything we experience in daily life. It does not push against surfaces or create wind. It operates on the geometry of spacetime itself, stretching the distances between galaxies without exerting any local force. One way to conceptualize this is through negative pressure. In ordinary fluids, pressure is positive. It pushes outward, resisting compression. But dark energy, if it is indeed a cosmological constant, exerts negative pressure. It pulls inward on itself in a way that, paradoxically, causes space to expand. This is not a contradiction, but a consequence of how general relativity links pressure to gravity. Positive pressure gravitates, adding to the attractive pull of matter. Negative pressure anti-gravitates, creating a repulsive effect. Dark energy's negative pressure is what drives the accelerated expansion. Yet calling it pressure may be misleading. Dark energy does not flow. It does not condense or evaporate, does not interact with matter or light. It simply is. It saturates every point in space with the same intensity, unchanging and ubiquitous. In this sense, it resembles a field knot, a field that varies from place to place, but one locked at a constant value throughout the universe. This field does not decay or dissipate. It does not lose strength over cosmic time. It is as present now as it was billions of years ago, and it will be as present billions of years hence. This permanence raises the deepest question of all. If dark energy is a property of space, and if space is expanding because of dark energy, where does the energy come from? Not in the sense of a source or reservoir, but in a more fundamental sense. What gives space this property? Why does empty space carry energy at all? Why does the vacuum have a non-zero baseline? These questions touch the limits of current physics. Quantum field theory predicts that the vacuum should have energy. But the predicted value is catastrophically wrong off by a factor of 10 to the power of 120, one of the largest discrepancies in all of science. Something is missing from our understanding, some principle or mechanism that sets the vacuum energy to the small but non-zero value we observe. Until we find it, dark energy remains a label for an observed phenomenon rather than an explanation. What we can say with certainty is that the universe is not static. It is not inert. Space is a substance with properties, and those properties dictate the fate of everything within it. The expansion we measure today is not a relic of the past, but an ongoing process driven by the nature of space itself. The universe grows because space wants to grow. And as it grows, it creates more of itself, weaving new distance into the fabric of reality with every passing moment. This is the mechanics of expansion. This is the engine that drives the cosmos apart, and it is only the beginning of the mystery. We are pattern-seeking creatures. Our brains evolved to detect edges and motion, to recognize faces in foliage, to predict where a thrown stone will land. Every instinct we possess was shaped by the demands of survival on a small, dense planet where objects have weight, where forces have direction, and where causes precede effects in ways we can observe directly. We understand the world through metaphor and comparison. We build models in our minds by relating the unfamiliar to the familiar. A river flows like time. An atom resembles a tiny solar system. Light behaves like a wave, or sometimes like a particle, depending on how we look at it. But some things resist comparison. Some phenomena exist so far beyond the scale of human experience that our intuitions not only fail to help us, they actively mislead us. Dark energy is one of these things. Consider the forces you encounter every day. Gravity pulls you toward the Earth. You feel its constant tug in your muscles, in the way objects fall when you drop them. Friction resists your motion when you push a heavy box across the floor. Electromagnetism holds atoms together, creates the light you see, generates the warmth of the sun on your skin. These forces have sources. Gravity comes from mass. Electromagnetism arises from charges and currents. Even when the mechanisms are invisible, the effects are local and immediate. Push something, and it moves. Stop pushing, and it stops. This is the physics of everyday life. It is the physics our ancestors needed to understand in order to survive. A falling branch could kill you. A thrown spear followed a predictable arc. Fire spread in ways that could be anticipated and controlled. The world made sense because it operated on principles we could test with our hands and eyes. Cause and effect were linked by proximity. Forces diminished with distance. If something moved, something else had pushed it. Dark energy violates all of these intuitions. It has no source in the ordinary sense. It does not emanate from a star or a black hole or a galaxy. It is not concentrated anywhere. It does not weaken as you move away from some point of origin, because there is no point of origin. It exists everywhere, uniformly, at all times. Every cubic meter of empty space contains the same amount of it, whether that space is in the void between galaxies or in the room where you sit. You cannot shield yourself from it. You cannot turn it off. You cannot even detect it locally because its effects only become apparent across distances so vast that human perception collapses into abstraction. This uniformity makes dark energy nearly impossible to visualize. When we think of energy, we imagine something dynamic, a fire burning, a battery discharging, a wave crashing. But dark energy does not flow or radiate or transfer. It does not move from one place to another. It simply is, saturating the fabric of spacetime like a dye dissolved uniformly in water. There are no gradients, no variations, no features to anchor our mental models. It is the flattest, most featureless phenomenon in the known universe, and our brains are not built to hold flat, featureless things in focus. Our cognitive toolkit is designed for the local and the tangible. We understand objects, not fields. We grasp particles, not geometries. The idea that space itself could have properties that emptiness could exert pressure, that a vacuum could push, contradicts the very concept of nothingness we carry from childhood. A vacuum, in everyday language, is the absence of something. It is what remains when you remove the air from a jar. It is negative space, a placeholder. To say that this placeholder has energy, that it acts, that it drives the largest scale motion in the cosmos, feels like a category error. It sounds like saying silence makes noise. This cognitive dissonance is not a failure of imagination. It is a feature of how our minds work. Human brains are prediction machines, constantly building models of the world based on patterns extracted from experience. When we encounter something that fits no existing pattern, we either force it into the nearest available category or we struggle to think about it at all. Dark energy fits no category. It is not like gravity, which pulls. It is not like radiation, which spreads. It is not like matter, which clumps. It is its own thing, and we have no evolutionary precedent for things that behave this way. There is also the problem of scale. Dark energy dominates the universe, but only on the largest scales. Within our solar system, within our galaxy, even within our local cluster of galaxies, its effects are negligible. Gravity binds these structures together far more strongly than dark energy can push them apart. If you could measure the acceleration of a single galaxy relative to another, the effect of dark energy would be real, but tiny, far too small to detect with human senses or even with most instruments over short time periods. It becomes measurable only when you look at the expansion of the universe as a whole. Comparing the distances to galaxies billions of light years away, this creates a profound disconnect between our lived experience and the fundamental dynamics of the cosmos. We spend our lives in a gravitationally dominated environment. Every force we feel, every motion we observe is shaped by gravity's pull or by electromagnetic interactions. Dark energy, meanwhile, operates in a regime utterly removed from our daily existence. It is like trying to understand the ocean by examining a single drop of water. The drop contains the same molecules, the same chemistry, but it reveals nothing of tides or currents or the pressure at depth. We are the drop, trying to infer the ocean. There is also a temporal problem. Human lifetimes are measured in decades. Civilizations endure for centuries or millennia. But the effects of dark energy unfold over billions of years. The acceleration of the universe has been ongoing for roughly the past 5 billion years, and it will continue for trillions more. This is a timescale so extended that it might as well be infinite from a human perspective. We cannot watch it happen in real time. We cannot conduct experiments that span its duration. We can only infer its presence by reconstructing the past through observations of distant light, piecing together a story written in redshifts and distances. This removes dark energy from the realm of direct experience entirely. It becomes a theoretical construct, a mathematical necessity inferred from data rather than a phenomenon we can point to and say, there it is. And humans are notoriously poor at accepting the reality of things we cannot perceive directly. We believe in the wind because we feel it. We believe in atoms because we see their effects in chemical reactions. But dark energy leaves no mark on our immediate surroundings. It does not shape the orbits of planets or the structure of molecules. It is cosmological, not personal. Our brains are also biased toward explanations that invoke agents and intentions. This is another legacy of evolution. In a world where predators and prey, allies and enemies, all acted with purpose, it was adaptive to assume that events had causes rooted in agency. A rustling in the bushes was not just winded, might be a threat. A pattern in the stars was not just geometry, might be a message. This cognitive bias, known as hyperactive agency detection, served our ancestors well. But it makes abstract, impersonal phenomena, like dark energy, feel incomplete. We want to ask, what is doing this? What wants the universe to expand? The answer that nothing wants it. That it is simply a property of space feels unsatisfying in a way that has nothing to do with logic and everything to do with how our minds frame causality. The history of cosmology reflects this struggle. For millennia, humans placed themselves at the center of the universe. The Earth was stationary, and the heavens revolved around it. This was not mere arrogance. It was the most reasonable interpretation of direct observation. The ground beneath our feet does not seem to move. The stars wheel overhead in predictable patterns. Without telescopes or mathematics, the geocentric model made perfect sense. It took centuries of careful measurement and intellectual courage to accept that our senses had misled us, that the Earth was not special, that we occupied no privileged position. Dark energy represents a similar challenge, but on a deeper level. It asks us to accept not only that our position in space is unremarkable, but that our intuitions about space itself are wrong. We must abandon the notion that empty space is passive. We must accept that the vacuum has structure, energy, dynamics. We must internalize the idea that the universe is not a container in which events unfold, but an active participant in those events. This is a conceptual leap that goes against every instinct honed by evolution. Part of the difficulty lies in language. We are forced to describe dark energy using words that carry baggage from other contexts. We call it energy, but it does not behave like any other form of energy we know. We say it pushes space apart, but there is no pushing in the mechanical sense. We describe it as a field, but it does not vary or ripple or interact. Every metaphor is imperfect. Every analogy breaks down. We are using a vocabulary designed for a three-dimensional world of objects and forces to describe a phenomenon that operates on the geometry of space-time itself. This linguistic inadequacy is not just a communication problem. It is a conceptual one. Language shapes thought. The words we have available constrain the ideas we can easily hold in our minds. When we lack precise terms for a phenomenon, we struggle to think about it clearly. Dark energy suffers from this constraint. It is neither dark nor, in the conventional sense, energy. The name is a placeholder, a label for our ignorance. But labels matter. They influence how we approach a problem, what questions we think to ask, what answers we deem plausible. There is also the issue of scale mismatch. Humans are medium-sized creatures. We are larger than atoms, smaller than planets. Our sensory systems evolved to detect phenomena at this intermediate scale: light waves our eyes can see, sound waves our ears can hear, temperatures our skin can tolerate. Anything too small or too large or too fast or too slow falls outside our perceptual range. We have built instruments to extend our senses: microscopes and telescopes, detectors and accelerators, but these tools provide data, not experience. We do not feel the quantum fluctuations in a vacuum. We do not see the expansion of space. We observe shadows and echoes of these processes, and from them we construct models. Dark energy exists at the extreme end of the scale spectrum. It is a cosmological phenomenon, operating across billions of light-years. It is also a vacuum phenomenon, tied to the smallest possible scales where quantum mechanics governs. This dual nature, simultaneously the largest and smallest thing in physics, makes it uniquely difficult to grasp. Our intuitions fail at both ends. We cannot visualize a billion light-years. We cannot imagine the roiling quantum foam of the vacuum. To understand dark energy, we must somehow bridge these scales in our minds, and our brains were never designed to do this. Another cognitive obstacle is the problem of unobservables. Science progresses by testing predictions against observations. We hypothesize, we experiment, we refine our models based on what we see. But dark energy cannot be observed directly. We cannot bottle it, measure it in a lab, or manipulate it. We can only observe its large-scale effects, the redshifts of distant galaxies, the patterns in the cosmic microwave background, the distribution of matter across the universe. From these indirect observations, we infer the presence of dark energy. This is a valid method. Science often proceeds this way, but it removes the phenomenon from the realm of the tangible. It becomes an abstraction, a number in an equation, rather than something we can point to in the world. Humans are also uncomfortable with mysteries that seem to expand rather than resolve. As we learn more about dark energy, we do not find simple answers. We find deeper questions. Is it a cosmological constant, fixed for all time, or is it a dynamic field that evolves? Does it interact with matter or radiation in ways we have not yet detected? Could it be a sign that our theory of gravity itself is incomplete? Each discovery opens new avenues of uncertainty. For minds that crave closure and coherence, this proliferation of questions can feel frustrating. We want the universe to make sense. We want the pieces to fit. Dark energy refuses to cooperate. There is also an emotional dimension to this difficulty. Dark energy determines the fate of the universe. If it remains constant, the universe will expand forever, accelerating into a cold, dark, dilute future where galaxies drift beyond each other's horizons and stars burn out one by one. This is not a comfortable thought. It lacks the drama of a big crunch, the cyclical comfort of an oscillating cosmos. It is an ending without resolution, a slow fading rather than a climax. Our narrative instincts rebel against this. We want stories with arcs, with turning points, with meaning. The story dark energy tells is one of inexorable dispersal, and that feels existentially unsatisfying. Yet perhaps the most profound barrier is the absence of a why. Science excels at answering how questions. How does the Earth orbit the Sun? How does genes encode information? How does space expand? But why questions are harder? Why does the universe exist at all? Why these laws of physics and not others? Why does empty space have energy? These questions edge into philosophy and metaphysics. They may not have scientific answers, at least not in the traditional sense, but humans cannot help asking them. We are meaning-making creatures. We need stories that explain not just the mechanism, but the reason. Dark energy offers no reason. It simply is. It is a feature of the universe, like the speed of light or the charge of an electron. Asking why space has this property is like asking why particles have mass or why time has a direction. The universe is under no obligation to align with our need for purpose. It operates according to principles that may be fundamentally impersonal, indifferent to our desire for narrative coherence. This is where the cognitive limits become most acute. We are trying to comprehend a phenomenon that offers no handhold for intuition, no anchor in experience, no clear purpose or origin. We are using brains shaped by millennia of navigating a world of rocks and trees and predators to map the behavior of a vacuum that spans cosmic voids. It is a mismatch of tool and task, and yet, remarkably, we have succeeded to some degree. We have detected dark energy. We have measured its effects. We've begun to constrain its properties. This is a testament not to the ease of the problem, but to the power of mathematics and observation to extend our minds beyond their natural limits. Still, the unease remains. Dark energy feels alien because it is alien, not in the sense of coming from elsewhere, but in the sense of being genuinely other. It is not made for us to understand intuitively. It is a reminder that the universe is larger, stranger, and more indifferent than our evolved perceptions can comfortably accommodate. And in that strangeness lies both a challenge and an invitation to push past the limits of what feels natural, and to see the cosmos as it is, rather than as we wish it to be. Albert Einstein did not believe in an expanding universe. When he completed his general theory of relativity in 1915, he had crafted a set of equations that described gravity not as a force, but as the curvature of space-time itself. Mass and energy told space-time how to curve. Space-time told mass and energy how to move. It was elegant, it was revolutionary, and it predicted something Einstein found deeply troubling. The equations suggested that the universe could not be static. Space itself, according to the mathematics, should either expand or contract. There was no stable middle ground. A universe filled with matter would collapse inward under its own gravitational pull, unless something counteracted that tendency. But in 1917, the idea of a dynamic universe seemed absurd. The cosmos, as far as anyone could tell, was eternal and unchanging. The stars had hung in the same configurations for as long as humans had watched them. The notion that the entire fabric of reality was growing or shrinking contradicted centuries of philosophical and scientific thought. Einstein faced a choice. He could trust the mathematics, accept that the universe was not static, and wait for observations to confirm or refute this prediction. Or he could modify the equations to match what seemed obvious, that the universe was stable. He chose the latter. He introduced a new term into his field equations, a constant that represented a kind of repulsive pressure inherent to space itself. He called it the cosmological constant, and he denoted it with the Greek letter lambda. The cosmological constant was not arbitrary. It fit naturally into the mathematical structure of general relativity. Einstein's equations related the curvature of spacetime to the distribution of energy and matter. But there was no reason, mathematically, that spacetime itself could not contribute to this energy budget. Lambda represented precisely this, a baseline energy density woven into the fabric of space. Present everywhere, at all times, unchanging, regardless of what matter or radiation might be around. With lambda in place, the equations balanced. The attractive pull of gravity was counteracted by the repulsive push of the cosmological constant. The universe could remain static, suspended in a delicate equilibrium. Einstein believed he had saved the cosmos from collapse. He had, in his view, corrected an oversight in his own theory. But the universe did not cooperate. Within a decade, Edwin Hubble's observations revealed that galaxies were receding from one another. The universe was expanding. Einstein's original equations had been correct all along. The cosmological constant, introduced to preserve a static cosmos, was unnecessary. Einstein later called it his greatest blunder. He removed lambda from his equations and moved on. Yet the cosmological constant did not disappear from physics. It lingered in the mathematics, a ghostly possibility. Even without it, general relativity allowed for a dynamic universe. Space could expand, driven by the initial conditions of the Big Bang. Gravity would slow this expansion over time, but it need not stop it entirely. For decades, cosmologists worked within this framework. They measured the rate of expansion, estimated the mass of the universe, and debated whether the cosmos would expand forever or eventually recollapse. Lambda seemed like a relic, a historical footnote. Then came the late 1990s. Two independent teams of astronomers studying distant supernova made an unexpected discovery. The universe was not just expanding, it was accelerating. Galaxies were moving apart faster now than they had billions of years ago. This was not what the standard models predicted. If only matter and radiation shaped the expansion, gravity should slow it down. Something else was at work. Something that exerted a repulsive influence strong enough to overcome gravity on cosmic scales. Physicists returned to Einstein's equations and found lambda waiting. The cosmological constant, once discarded as unnecessary, became the simplest explanation for the observed acceleration. If space itself carried a fixed energy density positive and constant, it would behave exactly as the observations suggested. As the universe expanded, more space came into being, and with it, more of this energy. The total amount of gravitating mass diluted as the universe grew, but the energy of the vacuum remained constant per unit volume. Eventually, vacuum energy would dominate and the expansion would accelerate. This reframing transformed the cosmological constant from a mathematical curiosity into a physical hypothesis. It was no longer just a term in an equation. It was a candidate for the substance driving the universe apart. Physicists began to call this substance dark energy, though lambda and dark energy are not quite synonyms. Lambda is a specific model of constant energy density that never changes. Dark energy is a broader concept that includes lambda, but also allows for other possibilities. Still, lambda remains the default, the simplest model that fits the data. But what does it mean for space to have energy? This is not an idle question. It touches the foundations of how we understand the vacuum. In classical physics, the vacuum was nothing in absence, a void. Remove all matter and radiation from a region of space, and what remains is empty. It has no properties. It exerts no influence. But quantum mechanics tells a different story. At the smallest scales, the vacuum is not empty. It seethes with activity. Quantum fields permeate all of space, and these fields fluctuate even in the absence of particles. Virtual particles, pairs of particles, and antiparticles flicker into existence and annihilate in intervals so brief they evade direct detection. These fluctuations are not speculative. They produce measurable effects, such as the Casimir force, where two metal plates placed close together in a vacuum experience a tiny attraction due to the disruption of vacuum fluctuations between them. These quantum fluctuations suggest that the vacuum has energy. Every field contributes to this energy. There are fields for electrons, for quarks, for photons, for every particle in the standard model of particle physics. Each field oscillates, even in its ground state, and this zero-point oscillation carries energy. Add up the contributions from all fields, and you get a prediction for the energy density of the vacuum. This is where theory and observation collide catastrophically, when physicists calculate the energy of the vacuum using quantum field theory. They arrive at a number that is absurdly large, roughly 10 to the power of 120. It's times larger than the observed value of dark energy. This is not a small discrepancy. It is not a factor of 2 or 10 or even a million. It is one of the largest mismatches between prediction and measurement in the history of science. If the vacuum energy were as large as quantum field theory suggests, the universe would have blown apart instantly. Galaxies, stars, planets, none of it could exist. Something is wrong. Either quantum field theory is missing a mechanism that cancels out most of this vacuum energy, leaving only the tiny residue we observe. Or general relativity needs modification at cosmological scales, or we are misunderstanding something fundamental about how quantum fields contribute to the energy of space. No one knows which. The cosmological constant problem, as it is called, remains one of the deepest unsolved puzzles in physics. Yet, despite this theoretical crisis, the cosmological constant works observationally. It fits the data from supernova, from the cosmic microwave background, from the large-scale distribution of galaxies. Lambda is not just a placeholder. It is a model that makes precise predictions, and those predictions match what we see. The universe behaves as if space has a small, positive, constant energy density. The mathematics of general relativity accommodates this seamlessly. The question is not whether lambda describes the acceleration it does. The question is why lambda has the value it has, and whether it is truly constant or something more dynamic. Einstein's equations allow for a cosmological constant, but they do not require it. Lambda can be set to any value, including 0, and the equations remain mathematically consistent. This freedom is unusual. Most constants in physics are fixed by deeper principles. The speed of light, the charge of an electron, the strength of gravity, these are not arbitrary. They are woven into the structure of physical law, determined by the symmetries and interactions of fields and particles. But lambda appears as a free parameter, a number that must be measured rather than derived. This arbitrariness is unsettling. It suggests that the cosmological constant is not fundamental but emergent, arising from some deeper mechanism we have yet to uncover. Or it suggests that our universe is one of many, each with a different value of lambda. And we happen to inhabit one where the value is small enough to allow structure to form. This latter possibility invokes the anthropic principle, the idea that the universe must be compatible with the existence of observers, because if it were not, you would not be here to wonder about it. The anthropic explanation is controversial. It shifts the question from why does lambda have this value to why does our universe have this value. It replaces a scientific puzzle with a statistical one. If there are countless universes with different values of lambda, then the fact that ours is suitable for life becomes a selection effect rather than a mystery. We observe a small cosmological constant, not because it is special, but because only universes with small values allow the formation of galaxies, stars, and ultimately, beings capable of asking questions. This explanation is intellectually unsatisfying to many physicists. It feels like giving up, like abandoning the search for a deeper principle. But it may also be correct. The multiverse is not ruled out by observation. And some theories of quantum gravity naturally predict a landscape of possible universes with varying physical constants. Lambda, in this view, is environmental rather than fundamental, a feature of our cosmic neighborhood, not a law of nature. Meanwhile, the energy of the vacuum remains mysterious, even in the simplest interpretation. If lambda is truly constant, then the vacuum has a fixed energy per unit volume. This energy does not dilute as space expands. A cubic meter of space today contains the same vacuum energy as a cubic meter of space a billion years ago. This constancy is built into the definition of lambda. It is a property of space itself, not of anything within space. But what gives space this property? One possibility is that the vacuum is the lowest energy state of all quantum fields. In quantum mechanics, every system has a ground state, a configuration of minimum energy. For a particle in a box, the ground state is the lowest allowed energy level. For a quantum field, the ground state is the vacuum. But even in the ground state, fields are not inert. They fluctuate. They hum with zero-point motion. This residual activity contributes energy, and if that energy is positive and does not average to zero, it manifests as a cosmological constant. The problem, as mentioned, is that the predicted vacuum energy is far too large. Quantum field theory lacks a mechanism to explain why the contributions from different fields do not simply add up to an enormous number. In principle, positive and negative contributions could cancel, leaving a tiny remainder. This is called fine-tuning, and it requires an extraordinary balance. The cancellation would need to be precise to more than 100 decimal places. There is no known symmetry or principle that would enforce such a cancellation. Some physicists have proposed that supersymmetry, a theoretical framework that pairs every particle with a heavier partner, might provide the necessary cancellation. In supersymmetric theories, the contributions to vacuum energy from bosons and fermions have opposite signs. If supersymmetry were exact, these contributions would cancel perfectly, leaving zero vacuum energy. But supersymmetry is not exact in our universe. It must be broken at some energy scale, and the breaking introduces corrections that, once again, predict a vacuum energy far larger than observed. Another approach is to question whether the cosmological constant is truly constant. Perhaps lambda is not a fixed number, but a slowly evolving field. This possibility is often called quintessence, named after the classical fifth element. In quintessence models, the energy of the vacuum changes over time, driven by a scalar field that rolls down a potential energy curve. Unlike lambda, which exerts constant pressure, quintessence can have a pressure that varies, and its energy density can decrease as the universe expands, though more slowly than matter or radiation. Quintessence introduces new questions. What is the field? What determines its potential? Why is it beginning to dominate now rather than in the distant past or future? These models are more flexible than a cosmological constant, but also more complicated. They require additional ingredients, additional parameters, and so far, observations have not provided compelling evidence that dark energy is anything other than constant. Lambda remains the simplest model that fits the data. There is also the possibility that dark energy is not a substance at all, but a signal that general relativity itself breaks down on cosmological scales. Just as Newton's gravity needed modification to account for the precession of Mercury's orbit, Einstein's gravity might need modification to account for the accelerated expansion. Theories of modified gravity attempt this by changing the left-hand side of Einstein's equations, the part that describes space-time curvature either, then adding lambda to the right-hand side, where energy and matter appear. Modified gravity theories are mathematically intricate and difficult to test. They must reproduce the successes of general relativity on smaller scales, predicting the orbits of planets, the bending of light, the behavior of black holes, while introducing new effects that become important across billions of light years. Most proposed modifications have been ruled out by observations, but the search continues. The advantage of modified gravity is that it avoids the vacuum energy problem entirely. The disadvantage is that it lacks the simplicity and elegance of lambda. Whatever the explanation, the cosmological constant has reclaimed its place in cosmology. Einstein introduced it to preserve a static universe, then discarded it when the universe proved dynamic. Now it has returned, not as a mistake, but as the leading explanation for why the universe is accelerating. Lambda fits the data. It satisfies the equations. 'Tis consistent with everything we observe. Yet it leaves the deepest questions unanswered. Why does the vacuum have energy at all? Why is that energy so small compared to what quantum field theory predicts? Why is it beginning to dominate the expansion now, roughly 14 billion years after the Big Bang, rather than much earlier or much later? These questions suggest that we are missing something: a principle, a symmetry, a deeper layer of understanding. The vacuum, once thought to be nothing, turns out to be the most pervasive thing in existence. It fills every corner of the universe. It exerts pressure. It shapes the fate of galaxies. And yet it remains, in many ways, as mysterious as it was when Einstein first introduced lambda over a century ago. We have learned to describe it mathematically. We have measured its effects. But we have not yet understood its origin. The cosmological constant is both the solution to the mystery of cosmic acceleration and the starting point for a deeper mystery one that may require entirely new physics to resolve. Light is a messenger. It carries information across the void, traveling at a fixed speed through the expanding fabric of space. Every photon that reaches our telescopes began its journey in the past, sometimes the recent past, sometimes the distant past. The light from the sun takes 8 minutes to arrive. The light from the nearest star beyond the sun takes over for years. The light from distant galaxies can take billions of years, crossing a universe that has changed profoundly during the photon's flight. This delay is not a limitation. It is an opportunity. By collecting ancient light, astronomers can observe the universe as it was, not as it is. Each observation is a window into history. A galaxy 10 billion light-years away appears as it existed 10 billion years ago, when the universe was younger, denser, and evolving at a different rate. By comparing observations of objects at different distances, we can reconstruct how the universe has changed over cosmic time. We can measure the expansion rate at various epochs. We can test whether that rate has remained constant or varied. But measuring cosmic distances is difficult. There are no mile markers in space. no rulers that stretch across intergalactic voids. We cannot send a probe to a distant galaxy and measure the distance directly. Instead, we must use indirect methods, relying on objects whose intrinsic brightness we understand. If we know how luminous an object truly is, and we measure how bright it appears from Earth, we can calculate how far away it must be. The relationship is simple. Apparent brightness decreases with the square of the distance. An object twice as far appears 4 times fainter. The challenge is finding objects whose intrinsic brightness is known what astronomers call standard candles. For centuries, this was a major obstacle. Stars vary wildly in their true luminosity. A red dwarf emits a fraction of the light of the sun. A blue supergiant outshines the sun by millions of times. Without knowing what type of star you are observing, you cannot determine its distance from its brightness alone. You need a class of objects that are both bright enough to be seen across vast distances and consistent enough in their properties that their true luminosity can be reliably inferred. Type Ia supernova are such objects. These are not the deaths of massive stars collapsing under their own gravity. Those events, called core collapse supernova, vary in brightness depending on the mass and composition of the progenitor star. Type Ia supernova arise from a different mechanism, one that produces remarkably uniform results. They occur in binary star systems where a white dwarf dense remnant of a sun-like star accretes matter from a companion. When the white dwarf's mass approaches a critical threshold, about 1.4 times the mass of the Sun, it can no longer support itself against gravity. The core ignites in a runaway thermonuclear explosion, obliterating the star entirely. This explosion is extraordinarily bright. For a few weeks, a single type Ia supernova can outshine an entire galaxy of hundreds of billions of stars. The light output is so immense that these events can be detected across billions of light-years. And because the explosion is triggered by a well-defined mass threshold, the peak brightness of type Ia supernova is remarkably consistent. They are not perfectly uniform. There are variations depending on the exact composition and rotation of the white dwarf. But these variations follow predictable patterns. Astronomers have learned to calibrate type Ia supernova, correcting for small differences and using them as precise distance indicators. In the 1990s, 2 independent teams of astronomers undertook an ambitious project. They set out to map the expansion history of the universe by observing type Ia supernova at various distances. The goal was to measure how the expansion rate had changed over billions of years. The expectation, based on decades of theoretical work, was that gravity would gradually slow the expansion. The universe had begun in a hot, dense state and had been expanding ever since. But the mutual gravitational attraction of all the matter within it should act as a brake. The question was whether this braking would be strong enough to eventually reverse the expansion, leading to a big crunch, or whether the universe would expand forever, albeit at a decelerating rate. The teams observed dozens of distant supernovae, measuring both their apparent brightness and their redshift. Redshift is a measure of how much the wavelength of light has been stretched during its journey through expanding space. When a galaxy emits light, that light has a specific wavelength determined by the atomic transitions within the galaxy's stars. But as the light travels through space, the expansion of space stretches the wavelength, shifting it toward the red end of the spectrum. The more the universe has expanded since the light was emitted, the greater the redshift. By measuring redshift, astronomers can determine how much the universe has grown during the light's travel time. The combination of brightness and redshift allows a direct test of cosmological models. If the expansion is decelerating, distant supernova should appear slightly brighter than expected, because the universe was expanding more quickly in the past and the light has traveled through less space than a constant expansion would predict. If the expansion is accelerating, distant supernova should appear slightly fainter, because the universe has expanded more than expected and the light has been diluted over a greater distance. The results were unambiguous. The distant supernova were fainter than predicted by a decelerating universe. Not by much the effect was subtle, but the pattern was clear and consistent across multiple observations. The universe was not slowing down. It was speeding up. The expansion rate was increasing over time. This was not what anyone had anticipated. It contradicted the most basic expectations of cosmology. Gravity pulls. It attracts. It should slow the expansion. Yet something was overpowering gravity, pushing space apart with increasing vigor. The discovery was met with skepticism. Could there be an error in the calibration of type Ia supernova? Could dust in intergalactic space be dimming the light, mimicking the effect of acceleration? The team scrutinized their data, repeated their analyses, and tested alternative explanations. But the evidence held. Other observations soon provided independent confirmation. Measurements of the cosmic microwave background, the afterglow of the Big Bang showed patterns consistent with a universe dominated by dark energy. Surveys of the large-scale distribution of galaxies revealed structures that matched the predictions of an accelerating expansion. Multiple lines of evidence converged on the same conclusion. The light from dying stars had revealed a hidden force. The universe was not coasting on the momentum of its initial expansion. It was being driven apart by something intrinsic to space itself, something that did not dilute as the universe grew. The simplest explanation was the cosmological constant's lambda, reborn. A fixed energy density in the vacuum, exerting negative pressure, causing space to expand faster and faster as more space came into being. The mathematics fit. The observations fit. Dark energy had moved from speculation to established fact. The process of measuring cosmic acceleration relies on precision. A type Ia supernova at a distance of billions of light-years appears as a faint smudge of light, barely distinguishable from background noise. Extracting useful information from such dim signals requires careful photometry measuring the intensity of light at different wavelengths over time. Astronomers must track the supernova as it brightens, peaks, and fades, constructing a light curve that spans weeks or months. The shape of this curve, combined with spectroscopic measurements that reveal the chemical composition and velocity of the expanding debris, allows the supernova to be classified and its intrinsic luminosity to be estimated. But the light has been altered during its journey. As it travels through billions of light-years of expanding space, not only is the wavelength stretched, but the rate at which photons arrive is also affected. Time itself is dilated by the expansion. A supernova that brightens and fades over the course of 20 days in its own rest frame appears to evolve more slowly when observed from Earth, the timescale stretched by the same factor as the wavelength. This time dilation is another signature of cosmic expansion, and it must be accounted for when analyzing distant supernova. There is also the issue of redshift measurement. The spectrum of a supernova contains absorption and emission lines features created by specific atoms absorbing or emitting light at characteristic wavelengths. These lines act as fingerprints, allowing astronomers to identify the elements present in the supernova's atmosphere. But in a distant supernova, these lines are shifted toward longer wavelengths. A line that appears in the ultraviolet when emitted might be observed in the visible range by the time it reaches us. By measuring the shift in wavelength, astronomers can calculate the redshift, which in turn reveals how much the universe has expanded since the light was emitted. Redshift is expressed as a dimensionless number, often denoted by the letter Z. A redshift of 0 means no expansion has occurred. The object is at rest relative to us. A redshift of 1 means the universe has doubled in size since the light was emitted. A redshift of 2 means it has tripled. The most distant supernova used to measure cosmic acceleration have redshifts around 1, meaning they exploded when the universe was roughly half its current size. These are not the most distant objects ever observed. Galaxies and quasars have been detected at much higher redshifts, but they occupy a crucial range for measuring the transition from deceleration to acceleration. This transition is the key insight. In the early universe, when matter and radiation were densely packed, gravity dominated. The expansion was decelerating, slowed by the mutual attraction of everything within the cosmos. But as the universe grew and matter spread out, its density decreased. The gravitational pull weakened. Meanwhile, if the energy density of the vacuum remained constant as the cosmological constant model predicts, then dark energy gradually became more important relative to matter. Eventually, dark energy overtook matter as the dominant influence on the expansion. This crossover happened relatively recently in cosmic history, roughly 5 billion years ago. Before that, the universe was decelerating. After that, it began to accelerate. Type Ia supernova allow us to observe this transition directly. By measuring supernova at different distances, we sampled different epochs. Nearby supernova show us the recent past, when acceleration dominates. More distant supernova show us an earlier era, when deceleration was still in effect. The change in behavior is encoded in the relationship between distance and redshift. If the expansion were constant, this relationship would be linear. If it were decelerating, distant objects would be slightly closer than a linear extrapolation would predict. If it is accelerating, distant objects are farther away. The data show acceleration. This conclusion rests on the assumption that type Ia supernova have remained consistent over cosmic time. If the explosions were systematically different in the past, brighter or fainter, the inferred distances would be wrong, and the evidence for acceleration would be compromised. This is a genuine concern, and astronomers have worked to test it. They have studied the properties of supernova at different redshifts, comparing their spectra, their light curves, their color evolution. So far, no significant evolution has been detected. Type Ia supernova at high redshift appear to be the same as those nearby, confirming that they are reliable standard candles across billions of years. There are other potential complications. Intergalactic space is not perfectly transparent. It contains dust, gas, and perhaps other forms of obscuring material. If distant supernova are preferentially dimmed by dust, they would appear fainter, mimicking the effect of acceleration. But dust has a characteristic signature. It dims blue light more than red light, causing objects to appear redder. Astronomers have looked for this signature in the supernova data and found that dust cannot explain the observed dimming. The effect is wavelength independent, consistent with increased distance rather than obscuration. Another concern is gravitational lensing. Light from a distant supernova can be bent and magnified by the gravitational fields of intervening galaxies and clusters. This can make the supernova appear brighter or fainter, depending on the alignment. For individual supernova, lensing effects are small and random, averaging out over large samples. But in principle, if there were a systematic bias in how lensing affects supernova at different distances, it could distort the inferred expansion history. Studies of lensing statistics suggest this is not a significant issue, but it remains an area of ongoing research. Beyond supernova, other methods corroborate the evidence for cosmic acceleration. One is the measurement of baryon acoustic oscillations, subtle ripples in the distribution of galaxies imprinted by sound waves in the early universe. These ripples provide a standard ruler for measuring cosmic distances, analogous to how supernova provide a standard candle. The distances inferred from baryon acoustic oscillations are consistent with those from supernova, independently confirming acceleration. Another method involves the cosmic microwave background. The temperature fluctuations in this radiation encode information about the geometry and composition of the universe. By analyzing these fluctuations, cosmologists can constrain the total energy density of the universe and the contributions from matter, radiation, and dark energy. The results align with the supernova measurements, pointing to a universe where dark energy comprises roughly 70% of the total energy. These complementary observations strengthen confidence in the reality of cosmic acceleration. No single piece of evidence is decisive on its own, but together they form a coherent picture. The universe is expanding, and that expansion is accelerating, driven by an energy component that does not dilute as space grows. The light from distant supernova was the first clear signal of this phenomenon, but it has since been confirmed by multiple independent techniques. The implications are profound. If acceleration continues indefinitely, the universe will grow exponentially. Distant galaxies will recede beyond the reach of observation, their light stretched to wavelengths we cannot detect. The cosmic horizon, the boundary of the observable universe, will shrink. Billions of years from now, galaxies outside our local group will have disappeared from view. And observers in that distant future will see a cosmos far emptier than the one we inhabit. The stars will burn out. Space will stretch into cold, dark isolation. This is the fate implied by a cosmological constant. But we do not yet know if the cosmological constant is the correct explanation. Dark energy could be dynamic, evolving over time, leading to a different future. It could strengthen, tearing the fabric of space apart in a big rip. It could weaken, allowing gravity to reassert itself. The evidence tells us that acceleration is happening now, but it does not guarantee what will happen next. The light from dying stars has shown us where the universe is going, but the final destination remains uncertain. The late 20th century was a time of confidence in cosmology. The Big Bang Theory had triumphed. The cosmic microwave background had been discovered, predicted, and measured with increasing precision. The expansion of the universe was established fact. Galaxies receded from one another, and the mathematics of general relativity described this recession with elegant simplicity. The remaining questions seemed tractable. How much matter did the universe contain? Would it expand forever, or would gravity eventually halt the growth and pull everything back into collapse? These were questions of measurement, not of fundamental uncertainty. Two competing visions shaped the debate. In one, the universe contained enough matter that gravity would eventually overcome the expansion. The cosmos would reach a maximum size, then contract, growing denser and hotter until it collapsed into a singularity, a big crunch, the mirror image of the Big Bang. In the other, the universe lacked sufficient matter to reverse the expansion. Space would grow forever, but gravity would slow the rate of growth asymptotically. Galaxies would drift apart, stars would burn out, and the universe would fade into darkness, but it would never collapse. Both scenarios assumed the same underlying principle. Gravity was the dominant force shaping cosmic evolution. No one seriously considered a third possibility. No one expected that the expansion might be speeding up. The idea of acceleration was not entirely absent from theoretical discussions. Einstein's cosmological constant allowed for it mathematically. A positive vacuum energy could, in principle, drive expansion at an increasing rate. But this seemed like a curiosity, a relic of Einstein's attempt to preserve a static universe. Most cosmologists assumed lambda was zero or negligibly small. There was no observational reason to think otherwise. And theoretical calculations suggested that if vacuum energy existed, it should either be zero or absurdly large, neither of which matched a universe that was expanding at a measured, moderate rate. The two teams that would append this consensus were not looking for dark energy. They were attempting to refine the measurement of cosmic deceleration. The Supernova Cosmology Project, led by Saul Perlmutter, and the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees. Both aimed to use Type Ia supernova to map the expansion history with unprecedented precision. The technique was well understood. The challenge was logistical: finding distant supernova, observing them before they faded, measuring their light curves and redshifts, and doing this for enough objects to achieve statistical significance. By the mid-1990s, both teams had accumulated data. They had observed dozens of supernova at distances corresponding to billions of light-years. The analysis was painstaking. Each supernova required careful calibration. Brightness had to be corrected for variations in the explosion itself, for the tilt of the host galaxy, for potential obscuration by dust. Redshift had to be measured accurately from spectroscopic observations. The relationship between distance and redshift had to be compared against theoretical models of different universes, those with high matter density, low matter density, with or without a cosmological constant. When the first results emerged, they were puzzling. The distant supernovae were fainter than expected, not by much, but consistently. If the universe were decelerating as anticipated, these supernovae should have appeared slightly brighter, because the light would have traveled through a universe that had expanded less than a constant rate would predict. Instead, they appeared dimmer, as if they were farther away than a decelerating model allowed. The implication was clear, but almost unthinkable. The universe was accelerating. The teams did not rush to announce this. They rechecked their calibrations. They tested for systematic errors. Could dust be dimming the supernova? Could there be an unknown population of dimmer-type IA explosions at high redshift? Could gravitational lensing be affecting the results? Every alternative explanation was explored. The data resisted all of them. The dimming was real, and it pointed unambiguously toward acceleration. In early 1998, both teams presented their findings. The Supernova Cosmology Project published their results in a paper that analyzed 42 higher redshift supernovae. The High Z Supernova Search Team followed with their own analysis of a complementary sample. The conclusions were identical. The expansion of the universe was not slowing down. It was speeding up. Something was pushing space apart with increasing force, overpowering the attractive pull of gravity. The reaction within the scientific community was a mixture of astonishment and skepticism. Acceleration implied the existence of a repulsive component in the universe, something that had never been directly observed. It resurrected the cosmological constant, a term that had been largely abandoned for decades. It suggested that 70% of the energy content of the universe was in a form no one understood, no invisible. Uniform field that exerted negative pressure and did not interact with matter or light. This was not a minor adjustment to cosmology. It was a fundamental reordering of what the universe was made of. The skepticism was not irrational. Extraordinary claims require extraordinary evidence. The effect was subtle, a difference of a few tenths of a magnitude in the brightness of distant supernova. Could there be an unknown systematic error? Could the data be explained by something less radical than a new component of the universe? Independent verification was essential. Other observers began their own searches for distant supernova. Theorists revisited the calculations, testing whether modified gravity or other exotic physics could account for the observations without invoking dark energy. But the evidence accumulated. More supernovae were observed, extending the distance range and improving the statistics. The pattern held. Nearby supernova, representing the recent past, fit the predictions of an accelerating universe. More distant supernova, representing an earlier epoch, showed signs of deceleration, exactly as expected, if dark energy had only recently come to dominate over matter. The transition from deceleration to acceleration was visible in the data, encoded in the subtle differences in brightness across cosmic time. Other lines of evidence began to align. Measurements of the cosmic microwave background provided an independent constraint on the total energy density of the universe. The geometry of space, as inferred from the angular scale of fluctuations in the microwave background, indicated that the universe was flat, neither open nor closed. But the amount of matter observed, both ordinary and dark, was not enough to account for a flat universe. Something else had to be present, something that contributed roughly 70% of the total energy. The supernova results filled this gap perfectly. Dark energy, in the form of a cosmological constant, provided the missing component. Surveys of the large-scale distribution of galaxies added further support. The clustering patterns of galaxies depend on the expansion history of the universe. A universe dominated by matter clusters differently than one dominated by dark energy. Observations matched the predictions of an accelerating cosmos. The pieces fit together. Supernova, the cosmic microwave background, and galaxy surveys all pointed toward the same conclusion. By the end of the decade, the initial skepticism had largely dissipated. The discovery of cosmic acceleration was accepted, though not fully understood. In 2011, Saul Perlmutter, Brian Schmidt, and Adam Rees were awarded the Nobel Prize in Physics for their work. The citation acknowledged that they had uncovered one of the deepest mysteries in modern science. The universe was not simply expanding, it was being driven apart by something that defied all prior expectations. The implications of this discovery extended far beyond the mechanics of expansion. It redefined the cosmic inventory. For centuries, astronomers had cataloged stars, galaxies, nebulae objects made of matter and light. Now, it appeared that all of this visible structure constituted less than 5% of the universe. Dark matter, invisible but gravitationally influential, accounted for another 25%. The remaining 70% was dark energy, a substance or field that had no precedent in physics. The term dark energy was itself a placeholder, a label for ignorance. It captured the essential mystery. This component was dark in the sense that it did not emit, absorb, or scatter light. It was energy in the sense that it contributed to the total energy budget of the universe. But beyond these broad features, almost nothing was known. Was it truly a cosmological constant, unchanging across time and space? Or was it something more dynamic, a field that evolved as the universe aged? The observations could not yet distinguish between these possibilities. The discovery also forced a reckoning with theoretical physics. Quantum field theory had long predicted that the vacuum should possess energy. Every quantum field contributes fluctuations, even in its lowest energy state, and these fluctuations carry energy. But when physicists calculated the expected magnitude of this vacuum energy, they arrived at a number so large it was incompatible with the observed universe. The discrepancy was not a factor of 2 or 10, but a factor of 10 to the power of 120. This was the cosmological constant problem, and the discovery of dark energy made it impossible to ignore. If the cosmological constant were as large as quantum field theory predicted, space would have exploded into exponential expansion long before stars or galaxies could form. The fact that the observed value was so small, yet still non-zero, suggested that some mechanism was at work, canceling out most of the vacuum energy but leaving a tiny residue. What that mechanism might be, no one knew. There was no known symmetry or principle in physics that would enforce such a cancellation. It seemed like an extraordinary coincidence, and coincidences in physics often signal deeper truths yet to be uncovered. The discovery also shifted the emotional tone of cosmology. Before 1998, the fate of the universe was a distant abstraction. Whether the cosmos would expand forever or eventually recollapse was a question for the far future. Billions or trillions of years hence. But acceleration changed the stakes. If dark energy remained constant, the universe would not just expand forever, would do so at an ever-increasing rate. This was not a gentle fading, but an exponential tearing apart of the cosmic fabric. The long-term consequences were sobering. As acceleration continued, distant galaxies would recede faster and faster, eventually crossing a horizon beyond which their light could no longer reach us. The observable universe would shrink. Galaxies outside our local gravitationally bound group would disappear from view. Their light stretched to wavelengths too long to detect. Future civilizations, if any arose, would look out into a cosmos that appeared almost empty. They would see only the stars of their own galaxy and a few neighbors surrounded by darkness. They would have no way to infer the existence of a larger universe. No evidence of the Big Bang, no record of the cosmic history we are privileged to observe. Closer to the present, the discovery raised questions about cosmic coincidence. Dark energy appears to have begun dominating the universe relatively recently, roughly 5 billion years ago. Before that, matter dominated and the expansion was decelerating. Why did the transition occur when it did? Why not in the early universe, when space was denser and hotter? Or in the far future, when galaxies had spread out even more? The fact that we live in the epoch when dark energy is just beginning to dominate seems remarkable. It suggests either that there is something special about this moment in cosmic history, or that dark energy is not constant, but evolving in a way that makes its dominance a temporary phase. This coincidence problem troubled many physicists. One response was the anthropic principle, the idea that we observe this particular epoch because earlier or later times would not have allowed observers to exist. If dark energy had dominated too early, galaxies would never have formed. If it dominates too late, we simply happen to live in the window where structure exists and intelligent life can arise. This explanation is logically consistent but philosophically unsatisfying. It replaces a question about mechanism with a statement about selection, which feels like giving up the search for deeper understanding. Another response was to propose that dark energy is not a constant but a field that evolves. These models, collectively called quintessence, allow the energy density of the vacuum to change over time. The field rolls slowly down a potential energy curve, its density decreasing as the universe expands, though more slowly than matter or radiation. In some quintessence models, the coincidence problem is alleviated because the field's evolution is tied to the matter density, ensuring that dark energy becomes important only after structure has formed. But quintessence introduces its own complications. It requires new fields, new potentials, new parameters, and so far, observations have not provided strong evidence that dark energy is anything other than a cosmological constant. The discovery also opened new avenues of research. Astronomers began designing surveys to measure the properties of dark energy with greater precision. They sought to determine whether its density was truly constant or whether it varied over time. This required observing supernovae at even greater distances, mapping the distribution of galaxies across larger volumes of space, and measuring the cosmic microwave background with finer resolution. Each of these efforts aimed to constrain the equation of state of dark energy, the relationship between its pressure and its density. A cosmological constant has a specific equation of state. Quintessence and other dynamic models have different signatures. By measuring this relationship, cosmologists hope to distinguish between possibilities. The discovery also influenced the search for a theory of quantum gravity. If dark energy is related to the vacuum energy predicted by quantum field theory, then understanding it requires a framework that unifies quantum mechanics and general relativity. String theory, loop quantum gravity, and other approaches to quantum gravity all make predictions about the vacuum. Though none has yet provided a satisfactory explanation for the observed value of the cosmological constant, the discovery of dark energy placed this problem at the center of theoretical physics, making it not just a curiosity but an urgent puzzle with observational consequences. There was also a cultural shift within the scientific community. Before 1998, cosmology was often seen as a field driven by theory, with observations serving to test grand ideas about the origin and fate of the universe. After 1998, it became clear that the universe could surprise us, that nature was not obligated to conform to our expectations. The discovery of acceleration was humbling. It reminded physicists that the cosmos is larger and stranger than our models suggest, and that the next breakthrough might come not from elegant mathematics, but from careful observation of the sky. The 1998 discovery did not answer where dark energy comes from. It did not explain why the cosmological constant has the value it does, or whether it is truly constant. It did not resolve the tension between quantum field theory and observation. But it established beyond doubt that dark energy is real, that it dominates the universe, and that it is accelerating the expansion. It transformed dark energy from a speculative idea into an observational fact, one that demands explanation. The universe is not winding down under the pull of gravity. It is being torn apart by an invisible force, and we are only beginning to understand what that means. The universe is not uniform. On the smallest scales, matter clumps into planets, stars, and galaxies. On the largest scales, galaxies themselves gather into clusters, and clusters form chains and sheets that stretch across hundreds of millions of light-years. Between these structures lie voids, vast regions, nearly empty of galaxies, dark expanses where space stretches uninterrupted. This pattern, known as the cosmic web, is the signature of gravity at work over billions of years. But gravity did not act alone. The cosmic web is the product of a contest between two opposing forces. One pulls matter together, gathering it into increasingly dense concentrations. The other pushes space apart, resisting the formation of structure and eventually dismantling what gravity has built. The first force is gravity itself, amplified by the presence of dark matter. The second is dark energy. The interplay between them determines not only the shape of the universe, but also its fate. In the beginning, gravity had the advantage. The early universe was hot, dense, and nearly uniform, but not perfectly so. Tiny fluctuations in density regions where matter was slightly more concentrated than average existed from the start. These fluctuations were imprinted during the first moments after the Big Bang, likely by quantum processes operating at scales far smaller than an atom. As the universe expanded and cooled, these small overdensities began to grow. Regions with slightly more matter exerted slightly more gravitational pull, attracting nearby material and becoming denser still. This feedback process, known as gravitational instability, drove the formation of structure. Dark matter played a crucial role. Ordinary matter, the protons, neutrons, and electrons that make up stars and planets, interacts with light and radiation. In the early universe, this interaction kept ordinary matter locked in a hot plasma, unable to clump efficiently. But dark matter does not interact with light. It feels only gravity. This allowed dark matter to begin collapsing into structures long before ordinary matter could follow. Dark matter formed the scaffolding, the invisible framework upon which galaxies would eventually assemble. As the universe expanded and cooled, ordinary matter decoupled from radiation and fell into the gravitational wells created by dark matter. Gas collected in these wells, cooled, condensed, and ignited into stars. Galaxies formed within halos of dark matter, each halo a concentration of invisible mass that held the visible matter together. Over time, these halos merged, building larger structures. Galaxies grouped into clusters, clusters aligned into filaments, filaments connected at nodes, forming the cosmic web. This process was not instantaneous. It unfolded over billions of years, shaped by the density of matter and the expansion of space. In regions where the initial overdensities were large, structure formed quickly. In regions where the overdensities were small, structure formed slowly or not at all. The result was a universe that was lumpy on large scales, dense in some places, nearly empty in others. The cosmic web reflects this hierarchy. The densest nodes are rich galaxy clusters containing thousands of galaxies bound by their mutual gravity. The filaments are chains of galaxies, tracing the paths where matter flowed during the collapse. The voids are regions where matter was sparse to begin with, and gravity had little to gather. But as the universe expanded, the balance shifted. The density of matter decreased. Galaxies and clusters spread farther apart. The gravitational pull that had driven structure formation weakened with distance. Meanwhile, if dark energy had a constant density as the cosmological constant model suggests, it did not dilute. Every cubic meter of space carried the same amount of dark energy, regardless of how much the universe had grown. The total influence of dark energy increased as more space came into being. This shift occurred gradually. For the first several billion years, matter dominated. The expansion was slowing, and gravity was winning. Structures continued to grow, building the cosmic web into an increasingly intricate network. But roughly 5 billion years ago, dark energy began to dominate. The expansion started to accelerate. Gravity's ability to pull matter together was gradually overpowered by the tendency of space itself to stretch. The consequences of this transition are subtle but profound. Acceleration does not reverse the formation of structures that already exist. Galaxies do not dissolve. Clusters do not fly apart. On local scales, where gravity is strong, the effects of dark energy are negligible. A galaxy cluster is held together by the mutual gravitational attraction of its member galaxies and the dark matter halo that surrounds them. This binding force is far stronger than the gentle push of dark energy. The cluster remains intact. But acceleration changes what happens on larger scales. It prevents new large structures from forming. As space expands faster, the distance between galaxy clusters grows, and the gravitational pull between them weakens. Clusters that might have merged in a matter-dominated universe instead drift apart in a dark energy-dominated one. The cosmic web stops evolving. The filaments no longer thicken. The voids no longer empty. The universe has reached a stage where its large-scale structure is frozen, unable to grow further because the expansion is too rapid. This marks a turning point in cosmic history. For billions of years, the universe became more structured, more differentiated, more interesting. Matter gathered into increasingly complex arrangements. Galaxies formed, stars ignited, planets coalesced, and on at least one of those planets, life emerged. All of this was possible because gravity could overcome the expansion, at least locally. But that era is ending. Dark energy ensures that the future will be less structured than the past, not more. The cosmic web will not grow denser. It will stretch, thin, and eventually fragment. The effect is already visible in simulations of cosmic evolution. Cosmologists use supercomputers to model the formation of structure over billions of years, starting from the initial conditions of the early universe, and evolving forward according to the laws of gravity and the expansion of space. These simulations reproduce the cosmic web in remarkable detail, matching the observed distribution of galaxies. But they also show what happens in a universe dominated by dark energy. The web stops growing. Filaments lose their coherence. Clusters become isolated islands, separated by ever-increasing distances. The universe becomes more homogeneous on large scales, approaching a state where structure exists only within gravitationally bound regions. This process is irreversible. Once dark energy begins to dominate, it does not relinquish control. As the universe expands, the density of matter continues to drop, while the density of dark energy remains constant. The ratio between them grows ever larger in favor of dark energy. Acceleration strengthens. The cosmic web, once a dynamic, evolving structure, becomes a relic of an earlier epoch. The cosmic web is not just a pattern in space, it is a record of cosmic history, a map of how matter has flowed over billions of years. By studying the distribution of galaxies, astronomers can infer the conditions of the early universe, the properties of dark matter, and the influence of dark energy. Each galaxy's position and motion carries information about the forces that shaped it. The cosmic web is a laboratory, and dark energy is one of its primary architects. One way to probe this influence is through the growth rate of structure. In a universe dominated by matter, overdense regions continue to grow denser over time. Gravity pulls matter inward, and the contrast between dense and empty regions increases. But in a universe dominated by dark energy, this growth slows and eventually stops. The acceleration of space counteracts the tendency of matter to clump. By measuring how fast structure is growing or failing to grow, astronomers can constrain the properties of dark energy. This measurement is challenging. It requires comparing the distribution of galaxies at different epochs, which means observing galaxies at different distances and therefore different times in the past. Surveys like the Sloan Digital Sky Survey have mapped millions of galaxies, revealing the cosmic web in exquisite detail. More recent projects, such as the Dark Energy Survey and the Euclid Space Telescope, extend these observations to greater distances and higher precision. They measure not just where galaxies are, but how they are moving, how they cluster, and how these patterns have evolved over cosmic time. One powerful technique involves baryon acoustic oscillations. These are subtle ripples in the distribution of galaxies, imprinted by sound waves that traveled through the hot plasma of the early universe. The ripples have a characteristic scale, roughly 150 million parsecs, or about 500 million light-years. This scale acts as a standard ruler, a known distance that can be compared across different epochs. By measuring how this ruler appears to stretch in observations of distant galaxies, astronomers can infer the expansion history of the universe. The results are consistent with a cosmological constant, confirming that dark energy has been accelerating the expansion for billions of years. Another technique uses weak gravitational lensing. Light from distant galaxies is bent as it passes through the gravitational fields of intervening matter. This bending distorts the shapes of galaxies, stretching and shearing their images in ways that depend on the distribution of mass along the line of sight. By analyzing these distortions across large areas of the sky, astronomers can map the distribution of dark matter, which dominates the gravitational lensing signal. These maps reveal how matter is clustered on large scales and how this clustering has evolved. The growth rate of structure inferred from lensing agrees with the predictions of a dark, energy-dominated universe. These observations paint a consistent picture. Dark energy is real. It dominates the universe, and it is actively shaping the cosmic web. But they also reveal something more subtle. The transition from matter domination to dark energy domination was not abrupt. It occurred gradually, over billions of years. During this transition, the cosmic web continued to evolve, but its evolution slowed. The largest structures galaxy superclusters, the largest known concentrations of matter are relics of an earlier time when matter still had the upper hand. New superclusters are not forming. The universe has passed the epoch of maximal structure formation. This has implications for the future of the cosmic web. As acceleration continues, the voids will expand faster than the filaments can bridge them. Galaxy clusters will drift farther apart, and the gravitational connections between them will weaken. Eventually, clusters outside our local group will recede beyond the cosmic horizon, the boundary beyond which objects move away faster than the speed of light. Their light will be stretched to infinitely long wavelengths, and they will disappear from view. The cosmic web will not break, in a dramatic sense, will simply fade, its components isolated by the relentless growth of space. Within gravitationally bound structures, dark energy has little immediate effect. Our galaxy, the Milky Way, is part of the local group, a small cluster that includes Andromeda and several dozen smaller galaxies. The local group is gravitationally bound. Its members orbit a common center of mass, and over the next few billion years, the Milky Way and Andromeda will merge, forming a larger elliptical galaxy. Dark energy will not prevent this. The gravitational pull between the two galaxies is strong enough to overcome the expansion of space. The same is true for other clusters. Galaxies within a cluster will continue to interact, merge, and evolve, unaffected by the accelerated expansion of the space between clusters. But beyond the local group, isolation is inevitable. The Virgo cluster, the nearest large galaxy cluster, is already receding from us. Its recession will accelerate, and eventually it will cross the cosmic horizon. The same will happen to every other cluster beyond our local neighborhood. Future observers, billions of years from now, will see a sky far emptier than the one we observe today. They will have no direct evidence of the cosmic web, no way to infer the existence of billions of other galaxies beyond their reach. They will live in a universe that appears small and static, unaware of the vast, dynamic cosmos that existed in earlier epochs. This isolation has philosophical implications. It suggests that our moment in cosmic history is privileged. We live at a time when the universe is old enough for structure to have formed, but young enough that the cosmic web is still visible. We can observe the afterglow of the Big Bang, measure the expansion of space, and map the distribution of galaxies across billions of light-years. Future civilizations, if any arise, will not have this privilege. They will inherit a universe that has been emptied by dark energy, a cosmos where the evidence of its own origin and evolution has been erased by the very force that drives its expansion. The contest between dark matter and dark energy is not symmetric. Dark matter builds. It gathers clumps and creates the conditions for stars and galaxies to form. Dark energy erases. It stretches, dilutes, and isolates. In the early universe, dark matter won and the cosmic web emerged. In the late universe, dark energy will win and the web will dissolve. We live in the transition, the brief epoch when both forces are significant, when the universe is structured but accelerating, complex but doomed to simplification. This is the role of dark energy in shaping the large-scale structure of the cosmos. It is not a builder, but a limiter, a force that sets an upper bound on how much structure can form and how long it can persist. It is the reason the cosmic web exists in its current form, and the reason it will not endure. Dark energy does not destroy galaxies or dismantle clusters. It does something more subtle and more profound. It ensures that the universe, having grown intricate and differentiated over billions of years, will return to simplicity. The cosmic web is a temporary pattern, a transient phase in the life of a universe driven apart by the energy of empty space. And that energy, quiet and invisible, is rewriting the geometry of everything. There is a number in physics that should not exist. It is so large, so incomprehensibly wrong, that it represents the most profound failure of prediction in the history of science. This number emerges when physicists attempt to calculate the energy of empty space using the principles of quantum mechanics. The calculation is straightforward. The assumptions are reasonable. The mathematics follows logically from well-tested theories, and the result is catastrophically incorrect. Quantum field theory tells us that the vacuum is not empty. Even in the absence of particles, fields exist. They permeate every point in space, and they fluctuate. These fluctuations are not optional or speculative. They are a fundamental feature of quantum mechanics arising from the uncertainty principle. A field cannot have both a perfectly defined value and a perfectly defined rate of change. It must oscillate, even in its lowest energy state. This oscillation carries energy. And when you add up the contributions from all the fields in nature, the electromagnetic field, the electron field, the quark fields, and so on, you arrive at a prediction for the energy density of the vacuum. The prediction is enormous. Depending on how the calculation is performed, the vacuum energy density comes out to be roughly 10 to the power of 120 times larger than the value inferred from observations of cosmic acceleration. This is not a small error. It is not off by a factor of 2 or 10 or even a million. It is off by a factor so large that it defies comprehension. If you wrote out the number in full, it would have more than 100 zeros. This discrepancy is known as the cosmological constant problem, or sometimes, more dramatically, as the vacuum catastrophe. The catastrophe is not just that the number is wrong. It is that if the number were correct, the universe as we know it could not exist. A vacuum energy density as large as quantum field theory predicts would have overwhelmed gravity from the very first moments after the Big Bang. Space would have expanded exponentially, far faster than the speed of light, driven by the immense repulsive pressure of the vacuum. No structures could have formed, no galaxies, no stars, no planets. Matter would have been torn apart before atoms could even assemble. The universe would have blown itself into oblivion in a fraction of a second. But that did not happen. The universe exists. Galaxies formed, stars ignited, life emerged. This means that the energy of the vacuum must be small, extraordinarily small, compared to what quantum field theory predicts. The observed value of dark energy, expressed as an energy density, is roughly 1 joule per cubic kilometer. This is tiny. It is so dilute that it has no measurable effect on anything smaller than a galaxy cluster. Yet, it is not zero. It is just large enough to accelerate the expansion of the universe, and no one knows why. The problem is not that quantum field theory is wrong. The theory has been tested to incredible precision in countless experiments. It predicts the magnetic moment of the electron to 12 decimal places. It describes the behavior of particles in accelerators with exquisite accuracy. It is one of the most successful theories in all of science. But when applied to the vacuum, it produces a prediction that is so far from reality that something fundamental must be missing. One possibility is that the contributions from different fields cancel out. Quantum field theory predicts that every field adds energy to the vacuum, but perhaps these contributions have different signs. Positive and negative contributions might nearly cancel, leaving only a tiny remainder. This is called fine-tuning, and it is a deeply unsatisfying explanation. The cancellation would need to be precise to more than 100 decimal places. There is no known symmetry or principle in physics that would enforce such a cancellation. It would require an extraordinary coincidence, as if the laws of nature had conspired to balance terms that have no reason to be related. Some physicists have proposed that supersymmetry could provide the necessary cancellation. Supersymmetry is a theoretical framework that pairs every particle with a heavier partner. In a supersymmetric universe, the contributions to vacuum energy from bosons and fermions would have opposite signs. If supersymmetry were exact, these contributions would cancel perfectly, leaving zero vacuum energy. But supersymmetry is not exact in our universe. It must be broken at some energy scale, and the breaking introduces corrections that, once again, predict a vacuum energy far larger than observed. Supersymmetry alleviates the problem but does not solve it. Another possibility is that our understanding of quantum field theory in curved spacetime is incomplete. General relativity describes gravity as the curvature of spacetime, and quantum field theory describes particles and fields in a fixed background. Combining the two is notoriously difficult. There is no complete theory of quantum gravity, and the vacuum energy problem may be a signal that such a theory is needed. Perhaps in the correct framework, the vacuum energy would be calculated differently, and the catastrophic prediction would disappear. String theory, one of the leading candidates for a theory of quantum gravity, offers some insight, but no definitive answer. In string theory, the vacuum is not unique. There are many possible vacuum states, perhaps as many as 10 to the power of 500. Each corresponding to a different configuration of the extra dimensions that the theory predicts. Each vacuum state has a different value of the cosmological constant. Some are positive, some are negative, and some are close to zero. This landscape of possibilities could explain the small observed value of dark energy as a statistical accident. We inhabit a universe with a small cosmological constant because such universes allow the formation of structure and the emergence of observers. This is the anthropic explanation, and it shifts the question from why is the cosmological constant small to why do we observe this particular universe. The anthropic explanation is controversial. It suggests that the value of the cosmological constant is not determined by fundamental laws, but by environmental factors, by which vacuum state our universe happens to occupy in a vast multiverse. This is unsettling to many physicists who prefer explanations rooted in necessity rather than chance. It also raises the question of whether the multiverse itself is testable or falsifiable, a requirement that some argue is essential for a scientific theory. Yet the vacuum catastrophe persists, unyielding to decades of effort. It is not just a puzzle. It is a signpost, indicating that something deep and fundamental is missing from our understanding. Either quantum field theory breaks down in ways we have not yet recognized, or general relativity requires modification at cosmological scales, or there is a new principal of symmetry, a mechanism, a deeper structure that we have yet to discover. The fine-tuning implied by the small observed value of dark energy is not the only example of this kind of problem in physics. The mass of the Higgs boson, the strength of the weak nuclear force, and the density of matter in the universe all appear to be finely tuned for the existence of complex structures. Adjust any of these parameters by a large factor, and the universe becomes inhospitable to life. Stars might not form, or they might burn out too quickly. Atoms might not be stable. Chemistry might not exist. The anthropic principle offers one response. We observe these values because we could not exist otherwise. But this does not explain why the values are what they are, only why we are here to observe them. The vacuum catastrophe exposes a rift between the physics of the very small and the physics of the very large. Quantum mechanics governs atoms, particles, and fields. General relativity governs spacetime, gravity, and the cosmos. Both theories are extraordinarily successful within their domains. But they are not compatible. They describe reality in fundamentally different ways, using different mathematical languages, different assumptions, different principles. The cosmological constant problem sits at the intersection of these two frameworks, and it reveals that neither can fully account for what the other predicts. Quantum mechanics is probabilistic and discrete. It deals with particles that exist in superpositions of states, where outcomes are determined only when measurements are made. It describes fields as collections of oscillators, each contributing energy even in the ground state. General relativity, by contrast, is deterministic and continuous. It describes spacetime as a smooth geometry that curves in response to energy and matter. In general relativity, the vacuum is simply the absence of energy, and matter it has no intrinsic properties beyond the geometry it inhabits. But quantum mechanics insists that the vacuum is alive with fluctuations, teeming with virtual particles that emerge and vanish in fractions of a second. When these two perspectives are combined naively, the result is nonsensical. Quantum field theory predicts that the vacuum has an enormous energy density. General relativity says that this energy should curve spacetime so drastically that the universe would be unrecognizable. Yet the universe we observe is nearly flat, its geometry only slightly curved by the presence of matter and dark energy. Something is wrong, but no one knows what. One response has been to argue that the vacuum energy calculated in quantum field theory is not the same as the cosmological constant in general relativity. Perhaps the vacuum energy does not gravitate in the way we expect. Perhaps there is a screening mechanism, some unknown effect that prevents the quantum fluctuations from contributing to the curvature of spacetime. This would require new physics modification of either quantum field theory or general relativity, or both. But no compelling mechanism has been found, and most proposals introduce new problems of their own. Another response is to question whether the vacuum energy is truly constant. In quantum field theory, the energy of the vacuum depends on the state of the fields. If the fields evolve over time, the vacuum energy could change as well. This is the basis of quintessence models, where dark energy is not a fixed cosmological constant, but a dynamic field that rolls down a potential. In these models, the vacuum energy was larger in the early universe and has decreased over time, approaching but never quite reaching zero. This evolution could explain why dark energy is currently small wee live, at a time when the field has nearly finished its descent. But quintessence does not resolve the vacuum catastrophe. It shifts the problem. Instead of explaining why the cosmological constant is small, it requires explaining why the quintessence field has the potential it does, why it started with the initial conditions it did, and why it is beginning to dominate now rather than in the distant past or future. The fine-tuning is displaced, not eliminated. There is also the possibility that the entire framework is wrong. Perhaps the vacuum does not have a well-defined energy in the way we think. Perhaps the concept of vacuum energy is an artifact of how we formulate quantum field theory, and a deeper theory would not predict such a thing at all. This is speculative, but it points toward the need for a more fundamental understanding of space, time, and quantum fields. Some physicists have suggested that the resolution lies in holography, the idea that the information content of a region of space is encoded on its boundary rather than in its volume. Holographic principles, inspired by the physics of black holes, suggest that spacetime itself is emergent, arising from more fundamental degrees of freedom. In such a framework, the vacuum energy might not be a sum over field oscillations, but something entirely different, a property of the boundary, or of the quantum information that underlies spacetime. This is an active area of research, but it remains far from producing a concrete solution to the cosmological constant problem. The vacuum catastrophe also raises questions about the nature of scientific explanation. In most areas of physics, theories are judged by their ability to make precise, falsifiable predictions. Quantum field theory excels at this. It predicts the outcomes of particle collisions, the behavior of atoms, the properties of materials. But when it comes to the cosmological constant, the prediction is spectacularly wrong. Does this mean the theory is fundamentally flawed? Or does it mean we are applying it incorrectly, extrapolating beyond its domain of validity? One lesson of the vacuum catastrophe is that physics is incomplete. Despite the remarkable successes of the 20th century relativity, quantum mechanics, the standard model of particle physics, there are questions we cannot answer. We do not know how to unify gravity and quantum mechanics. We do not know what dark matter is. We do not know why the cosmological constant has the value it does. These are not minor gaps in knowledge. They are foundational mysteries, suggesting that the next revolution in physics will be as profound as those that came before. The existence of the vacuum catastrophe also reminds us that the universe does not care about our theories. It does what it does, regardless of whether we can explain it. The cosmological constant is small. Dark energy drives the accelerated expansion. These are facts established by observation. The challenge for physics is to construct a theory that accommodates these facts without resorting to fine-tuning or appeals to chance. Whether such a theory exists and whether we are capable of discovering it remains an open question. In the meantime, the vacuum catastrophe stands as a monument to our ignorance. It is a reminder that the universe is stranger than our equations suggest, that the fabric of reality operates according to principles we have yet to grasp. The energy of empty space, once thought to be zero or irrelevant, turns out to be one of the most important quantities in cosmology. It shapes the fate of the universe, determines the future of galaxies, and challenges our deepest theories of nature. And yet we do not know where it comes from, why it has the value it does, or what it truly is. The vacuum is not empty. 'Tis full of fields, full of energy, full of mystery. And that mystery, more than a century after Einstein introduced the cosmological constant, remains as profound as ever. The catastrophe is not in the vacuum itself, but in our understanding. The universe works. It expands, accelerates, and allows structure to form within precise limits. We simply do not yet know why. Physics has a history of revealing forces where none were suspected. Electricity and magnetism, once thought to be separate phenomena, merged into a single electromagnetic force. The weak nuclear force, responsible for radioactive decay, was unified with electromagnetism into the electroweak interaction. Gravity itself was reimagined by Einstein not as a force pulling objects together, but as the curvature of spacetime around mass and energy. Each unification brought clarity, showing that what appeared complex was actually simple, that what seemed disconnected was deeply related. Dark energy may be the next chapter in this story. It may not be a substance at all, but a signal of evidence that our current theories are incomplete, that the laws governing the cosmos require revision. The question is not merely where dark energy comes from, but what it is. Is it a new field, a fifth fundamental force beyond gravity? electromagnetism, and the strong and weak nuclear forces? Or is it a property of gravity itself, a modification that becomes apparent only at the largest scales? The answer could reshape our understanding of reality. One possibility is that dark energy is dynamic rather than constant. This hypothesis, often called quintessence, proposes that dark energy is not the cosmological constant, but a scalar field of quantity that has a value at every point in space and evolves over time. Scalar fields are familiar in physics. The Higgs field, which gives particles their mass, is a scalar field. Inflation, the rapid expansion thought to have occurred in the first moments after the Big Bang, is driven by a scalar field called the inflaton. Quintessence would be another such field, but one whose influence becomes significant only in the late universe. In quintessence models, the energy density of this field changes as the universe expands. Unlike the cosmological constant, which maintains a fixed density regardless of how much space grows, quintessence can dilute or increase depending on the shape of its potential energy curve. The field rolls slowly down this curve, like a ball descending a gentle slope. The rate at which it rolls determines how the energy density changes, and this in turn affects the expansion rate of the universe. If the field is rolling slowly enough, it mimics a cosmological constant over observable timescales, explaining why dark energy appears constant in current measurements. Quintessence has appeal because it avoids the fine-tuning problem, at least partially. The cosmological constant requires an explanation for why its value is so small. Quintessence shifts the question to why the field has the potential it does, and why it began with the conditions necessary to produce the observed acceleration. These are still difficult questions, but they are potentially answerable within a broader theoretical framework. Quintessence could arise naturally in theories of quantum gravity, such as string theory, where many scalar fields are predicted to exist. The challenge with quintessence is that it makes predictions that differ only subtly from those of a cosmological constant. The field's energy density changes slowly. So, over the span of observable cosmic history, the differences are small. Distinguishing quintessence from a cosmological constant requires extremely precise measurements of the expansion rate at different epochs. Surveys of distant supernova, baryon acoustic oscillations, and gravitational lensing are all being used to constrain the equation of state of dark energy, the relationship between its pressure and density. So far, the data are consistent with a cosmological constant, but they do not rule out slowly evolving quintessence. Another possibility is that dark energy is not a substance, but a symptom of modified gravity. General relativity has been tested extensively within the solar system, around black holes, and in binary pulsar systems. It passes every test with remarkable precision, but these tests probe gravity on relatively small-scale distances of light years, or less. On cosmological scales, spanning billions of light years, gravity has never been tested with the same rigor. What if general relativity breaks down at these distances? What if the equations that describe the curvature of spacetime need additional terms? Corrections that become significant only when applied across the entire observable universe. Modified gravity theories attempt this. They alter the left-hand side of Einstein's field. Equations the part that describes how spacetime curves, rather than adding dark energy to the right-hand side, where matter and energy appear. One such theory, called FR gravity, generalizes general relativity by allowing the curvature of spacetime to affect the dynamics in more complex ways. In these models, the accelerated expansion is not caused by a mysterious energy filling space, but by a change in how gravity itself operates on large scales. The advantage of modified gravity is that it eliminates the need for dark energy entirely. The acceleration is a geometric effect, a consequence of the way spacetime responds to the distribution of matter. The disadvantage is that these theories are highly constrained by observations. They must reproduce all the successes of general relativity on smaller scales while introducing new behavior on cosmological scales. Many proposed modifications have already been ruled out by observations of gravitational waves, the orbits of planets, and the distribution of galaxies. The remaining viable models are few, and they face challenges in explaining not just the accelerated expansion, but also the growth of structure and the properties of the cosmic microwave background. There is also the possibility that dark energy is a window into extra dimensions. String theory, one of the leading candidates for a unified theory of quantum gravity, predicts that space has more than 3 dimensions. The extra dimensions are thought to be compactified, curled up so tightly that they are invisible at everyday scales. But they could still influence the behavior of gravity and other forces. If dark energy arises from the geometry or dynamics of these extra dimensions, it would link cosmology to the deepest levels of theoretical physics. In some models, the extra dimensions are not static, but evolving. As the universe expands, the size or shape of the extra dimensions could change, and this evolution could manifest as dark energy in our 3-dimensional space. Alternatively, the presence of brane higher dimensional surfaces on which our universe might reside could introduce new forces or fields that appear to us as dark energy. These ideas are speculative, but they illustrate how dark energy could be a clue to physics beyond the Standard Model and general relativity. Another intriguing hypothesis is that dark energy reflects a multiverse. In this view, the cosmological constant is not determined by a fundamental principle, but by environmental factors. String theory predicts a vast landscape of possible vacuum states, each with a different value of the cosmological constant. The universe, or more precisely, the multiverse, samples all these possibilities. Then we find ourselves in a region where the cosmological constant is small, simply because larger values would not allow galaxies, stars, or observers to exist. This is the anthropic explanation, reframed in the context of a multiverse. The multiverse hypothesis is polarizing. To some, it represents a profound shift in how we think about physical laws, as universal and inevitable, but as contingent and local. To others, it feels like an abandonment of the search for deeper explanations, a retreat into untestable speculation. Whether the multiverse is science or philosophy depends on whether it can make predictions that distinguish it from other models. Some researchers are working on ways to test multiverse scenarios indirectly, through patterns in the cosmic microwave background or the distribution of vacuum states in string theory. But consensus is far from reached. What unites all these ideas? Quintessence, modified gravity, extra dimensions. The multiverse, the recognition that dark energy is not just a mystery to be solved, but a doorway. It points toward new physics, toward a more complete understanding of the universe. The cosmological constant problem, the vacuum catastrophe, the accelerated expansion, these are not isolated puzzles. They are symptoms of a deeper incompleteness in our theories. The search for the identity of dark energy is also a search for the next fundamental theory. Just as Einstein's general relativity revealed that Newton's gravity was an approximation, valid in weak fields and at low speeds, the theory that explains dark energy will likely reveal that general relativity itself is an approximation. The question is what lies beyond. One clue comes from the intersection of quantum mechanics and gravity. General relativity is a classical theory. It describes spacetime as a smooth, continuous geometry, with no reference to the quantum fluctuations that dominate the microscopic world. Quantum mechanics, meanwhile, treats particles and fields probabilistically, with superpositions and uncertainties that have no counterpart in classical geometry. These two frameworks have never been successfully unified. Attempts to quantize gravity to treat spacetime itself as subject to quantum rules lead to mathematical inconsistencies and infinities that cannot be easily removed. Dark energy may be a clue to how this unification should proceed. The energy of the quantum vacuum, as calculated in quantum field theory, is a prediction about the state of space itself. But general relativity, which describes how energy curves spacetime, cannot accommodate this prediction without producing absurd results. The vacuum catastrophe is not just a numerical discrepancy. It is a conceptual conflict between two pillars of modern physics. Resolving it will require a framework that treats space-time and quantum fields on equal footing. String theory offers one such framework. In string theory, particles are not point-like, but extended objects' tiny loops of energy vibrating at different frequencies. Gravity emerges naturally from string theory as one of the vibrational modes. The theory also predicts extra dimensions, supersymmetry, and a vast landscape of possible vacuum states. But string theory is not yet a complete or testable theory of everything. It makes few concrete predictions about dark energy, and the landscape of vacua introduces its own problems, including the question of why our universe occupies the particular vacuum state it does. Loop quantum gravity takes a different approach. Instead of starting with strings, it quantizes space-time itself, treating it as a network of discrete loops and nodes at the Planck scale, the smallest scale where quantum effects of gravity become important. In this framework, space is not continuous but granular, composed of fundamental units of volume and area. Dark energy could emerge from the collective behavior of these quantum grains, much as temperature emerges from the motion of molecules. But loop quantum gravity is also incomplete, and it has not yet produced a satisfactory explanation for the cosmological constant. Another approach is emergent gravity. The idea that space-time and gravity are not fundamental but arise from more basic ingredients. In some versions, space-time is an emergent phenomenon, similar to how the properties of water emerge from the interactions of molecules. Gravity, in this view, is not a fundamental force, but an effective description of something deeper, perhaps the entanglement of quantum information, or the thermodynamics of horizons. If gravity is emergent, then the cosmological constant might not be a property of spacetime itself, but a feature of the underlying degrees of freedom from which spacetime arises. These ideas are speculative, but they reflect a shift in thinking. Dark energy is no longer seen merely as a component of the universe to be measured and catalogued. It is viewed as evidence that our current theories are provisional, that the map we have drawn of reality is missing entire continents. The accelerated expansion is a signpost pointing toward physics that has not yet been discovered. There is also the possibility that dark energy is not one thing, but many. Perhaps the cosmological constant provides a baseline, and on top of it, dynamic fields like quintessence contribute additional effects. Or perhaps different regions of the universe have different values of dark energy, separated by boundaries or phase transitions that we cannot detect from our vantage point. The universe could be far more complex than the homogeneous isotropic models we use to describe it. Dark energy might vary from place to place, from epoch to epoch, in ways that future observations will reveal. Current and future experiments are designed to probe these possibilities. Satellites like the Euclid Space Telescope and the Nancy Grace Roman Space Telescope will map the distribution of galaxies and measure the expansion. History with unprecedented precision. Ground-based surveys like the Vera Rubin Observatory will observe millions of supernova and gravitational lenses, constraining the properties of dark energy over a wide range of distances. Gravitational wave observatories may detect signals from the early universe, offering clues about the vacuum energy during inflation and how it relates to the dark energy we observe today. These measurements will not necessarily reveal the origin of dark energy, but they will narrow the possibilities. If the equation of state of dark energy is found to change over time, quintessence becomes more plausible. If the expansion history deviates from the predictions of general relativity, modified gravity gains support. If no such deviations are found, the cosmological constant remains the simplest explanation, and the focus shifts to understanding why it has the value it does. Whatever the answer, dark energy has already transformed cosmology. It has revealed that the universe is more than stars, galaxies, and dark matter. It has shown that the vacuum, the most featureless, uniform aspect of reality, plays a central role in shaping the cosmos. It has forced physicists to confront the limits of their theories and to consider ideas that once seemed too radical or speculative. Dark energy is the universe telling us that we do not yet understand the rules. It is a reminder that nature is under no obligation to match our expectations, that the cosmos operates according to principles we are still uncovering. The search for its origin is not just a scientific endeavor. It is an intellectual journey into the unknown, a quest to see beyond the visible and the measured, to glimpse the deeper structure of reality. In the end, the question, where does dark energy come from, may not have a simple answer. It may require a new language, a new mathematics, a new way of thinking about space, time, and energy. It may demand that we let go of assumptions we have held for decades or centuries, and accept that the universe is stranger and richer than we imagined. But this is how science progresses, not by confirming what we already believe, but by confronting what we do not understand. Dark energy is the frontier, and the frontier is where the deepest truths are found. The universe will not end in fire. There will be no final collision, no cataclysmic implosion, no moment when everything rushes back together in a mirror image of the Big Bang. The cosmos will not die suddenly. It will fade, slowly, inexorably, over trillions of years. The stars will burn out, the galaxies will drift beyond the horizon of observation, and space itself will stretch into a cold, dark vastness where nothing new can ever form. This is the fate written by dark energy. If dark energy remains constanta cosmological constant, unchanging across time, the acceleration of the universe will continue indefinitely. The expansion will not merely persist, it will intensify. Distant galaxies, already receding from us at speeds approaching the velocity of light, will cross a boundary beyond which their light can no longer reach us. This boundary is called the cosmic event horizon, and it functions much like the event horizon of a black hole. Once an object crosses it, no signal from that object can ever arrive. The galaxy does not disappear in a dramatic sense. It simply fades, its light stretched to wavelengths so long that no detector could register them. To future observers, it will be as if the galaxy never existed. This process has already begun. The most distant galaxies we can observe today are receding faster than the speed of light, carried away not by motion through space, but by the expansion of space itself. We can still see them because the light they emitted billions of years ago is only now reaching us, having traveled through a universe that was smaller and expanding more slowly at the time. But the light they emit today will never reach us. The expansion is too rapid. The distance is growing too fast. Those galaxies are, in a real sense, already lost. Billions of years pass, more galaxies will cross this horizon. The observable universe will shrink. Today, we can see roughly 2 trillion galaxies spread across a sphere of space, some 93 billion light-years in diameter. In 1 trillion years, an observer in our galaxy, if any, will see far fewer. The Virgo cluster, the nearest large concentration of galaxies, will have drifted beyond reach. The distant superclusters that currently trace the cosmic web will have vanished. The sky will darken, not because the galaxies have extinguished, but because their light can no longer traverse the expanding gulf between us. Eventually, only the galaxies gravitationally bound to our own will remain visible. The Milky Way and Andromeda will have merged by then, forming a single elliptical galaxy. The smaller galaxies of the local group will have been absorbed or scattered. This combined galaxy will be an island, isolated in a vast ocean of expanding space. Beyond its boundaries, the universe will appear empty. The cosmic microwave background, the faint afterglow of the Big Bang, will have been stretched to wavelengths so long that it becomes undetectable. The evidence of the universe's fiery origin will have been erased by the very expansion it set in motion. Future astronomers, if they exist, will face a cosmos that offers no clues to its history. They will see stars within their galaxy orbiting in predictable patterns. They will measure the gravitational pull of dark matter holding the galaxy together. But they will have no way to infer the existence of a larger universe beyond. No distant galaxies to observe. No redshifts to measure. No cosmic microwave background to study. The expansion of space, the Big Bang, the existence of dark energy, all of this will be invisible to them. They will live in a universe that appears static, small, and eternal, much as humans once believed before the 20th century. This is one of the great ironies of cosmology. We live in a privileged epoch. The universe is old enough that structure has formed galaxies, stars, planets, life. But it is young enough that the evidence of cosmic history is still visible. We can observe the cosmic microwave background, measure the redshifts of distant galaxies, detect the acceleration driven by dark energy. We can piece together the story of how the universe began, how it evolved, and where it is heading. Future civilizations will not have this privilege. The universe will have moved on, leaving them in a cosmos scrubbed clean of its past. The stars themselves will not last forever. The smallest, coolest stars' red dwarf scan burn for trillions of years, fusing hydrogen with miserly efficiency. But eventually, even they will exhaust their fuel. Larger stars have already come and gone, their lifetimes measured in millions or billions of years. The Sun will expand into a red giant in roughly 5 billion years, engulfing the inner planets before collapsing into a white dwarf. Over time, all stars will follow similar paths. Some will end as white dwarfs, slowly cooling into black dwarfs cold, dark remnants emitting no light. Others will collapse into neutron stars or black holes, but none will shine forever. As the last stars fade, the universe will be left with the remnants. Black holes will be the longest-lived objects, persisting for timescales that dwarf the current age of the universe. A black hole with the mass of the Sun will take 10 to the power of 67 years to evaporate through Hawking radiation, a process so slow it is almost inconceivable. Supermassive black holes, millions or billions of times more massive, will take even longer. But they too will eventually radiate away, leaving behind only photons and particles scattered across an ever-expanding void. By this time, the universe will have reached a state sometimes called the heat death. It will not be hot in the conventional sense. It will be cold, approaching absolute zero. The term refers to the thermodynamic state where entropy, the measure of disorder, has been maximized. No energy gradients will remain. No stars will burn. No processes will generate useful work. The universe will be uniform, featureless, and inert. Space will continue to expand, but there will be nothing within it to observe the expansion. This future is not certain. It depends on the assumption that dark energy remains constant. If dark energy is not a cosmological constant but a dynamic field, the fate of the universe could be different. If the field strengthens over time, the expansion could accelerate beyond what we observe today, eventually tearing apart galaxies, stars, planets, and even atoms. This scenario, known as the Big Rip, would end not in a whimper, but in a violent disintegration of all structure. Alternatively, if dark energy weakens, the expansion could slow and gravity might reassert itself. The universe could halt its growth, or even reverse, collapsing back into a big crunch. But current observations suggest neither of these extremes. The data are consistent with a cosmological constant, pointing toward the long, slow fade of heat death. There is something profoundly humbling about this vision of the future. The universe is not made for us. It does not preserve our knowledge or protect the conditions that allowed us to exist. Dark energy does not care about galaxies or stars or the fleeting civilizations that might arise within them. It simply is a property of space, indifferent to the structures it will eventually erase. We are witnessing a universe in transition, a brief moment of complexity between the formless simplicity of the early cosmos and the cold uniformity of the far future. Yet there is also something remarkable in the fact that we are here to witness it. consciousness emerged in this universe against improbable odds, at a time when the cosmos is still rich with structure and information. We have looked out into the void and seen not just stars, but the architecture of space-time itself. We have measured the expansion, traced the history of matter, and identified the invisible forces that shape reality. We are the universe becoming aware of itself, if only for a moment. This awareness is fragile. The window in which civilizations can observe the broader cosmos is narrow in cosmic terms. Humanity has existed for a few 100,000 years. We have understood the expansion of the universe for less than a century. In another 100 billion years, the evidence we rely on distant galaxies, the cosmic microwave background, the patterns of large-scale structure will have faded. Future observers will not have access to the clues we take for granted. They will inherit a universe that has forgotten its origins. This makes our moment unique. We live at a time when the universe is both complex enough to produce observers and transparent enough to reveal its secrets. We can see the afterglow of the Big Bang. We can measure the acceleration driven by dark energy. We can infer the presence of dark matter from the motion of galaxies. We have access to the full narrative of cosmic history from the first moments of existence to the present day. This is not a privilege that will last. The universe is already beginning to hide its past, and over time, it will hide more. The realization that our knowledge is temporary adds weight to the questions we ask. Where does dark energy come from? What is the nature of the vacuum? Why does the universe have the properties it does? These are not idle curiosities. They are questions about the fundamental structure of reality, asked at the only time in cosmic history when they can be answered through direct observation. If we do not find the answers now, or if we do not pass our knowledge forward, future generations may never have the opportunity to ask. There is also a deeper question, one that science alone cannot fully address. What does it mean to live in a universe governed by dark energy? We have always sought meaning in the cosmos' patterns, purposes, connections between ourselves and the stars. Ancient cultures saw the heavens as a realm of gods and fate. Early scientists saw clockwork precision, a universe of predictable laws. Modern cosmology has revealed something stranger universe that is vast, impersonal, and dominated by forces we do not understand. Dark energy is the clearest symbol of this strangeness. It is the largest component of reality, yet it interacts with nothing. It drives the expansion, yet it has no source. It shapes the future, yet it offers no purpose. Some find this unsettling. A universe driven by dark energy is one without inherent meaning, without a center, without a destination. It expands not toward anything, but simply because expansion is what space does. There is no grand design, no final state, no reason beyond the laws of physics. This can feel like a loss, a universe emptied of significance. But others find liberation in this. If the universe offers no prescribed meaning, then meaning becomes something we create. Our existence is not determined by cosmic purpose, but by chance, by the particular arrangement of matter and energy that allowed structure to form and life to emerge. We are not central to the universe, but we are part of it. We are made of the same atoms forged in stars, governed by the same forces that shape galaxies. Our thoughts, our questions, our observations, these are expressions of the universe itself. Reflecting on its own nature, dark energy ensures that this reflection is temporary. The universe will outlast us by unimaginable spans of time. Long after the last human has vanished, long after the Earth has been consumed by the dying sun, long after the Milky Way has merged with Andromeda and the local group has become a solitary island, the expansion will continue. Space will stretch, the cosmic horizon will shrink, while the stars will fade. And eventually, there will be nothing left but cold, dark, empty space, expanding forever into a future without events. But we are here, now. We have seen the universe at its most revealing. We have measured the light from distant supernova and traced the curvature of spacetime. We have detected the cosmic microwave background and mapped the distribution of galaxies. We have identified dark matter and dark energy, even if we do not yet understand them. We have glimpsed the machinery of the void, the forces that will shape the cosmos for trillions of years to come. This knowledge will not save us from the fate dark energy has written. It will not slow the expansion or halt the heat death, but it is its own kind of triumph. We are small, brief, fragile creatures on a small, brief, fragile world. Yet we have looked beyond ourselves and seen the universe as it is. We have asked where dark energy comes from, even knowing the answer may lie beyond our reach. We have confronted the void and mapped its contours. We have understood, if only partially, the engine that drives the cosmos apart. And in doing so, we have done something the universe itself cannot do. We have given it witness. We have taken the impersonal forces of expansion and acceleration and translated them into knowledge, into questions, into stories. We have made meaning from the meaningless. We have found beauty in the equations, wonder in the observations, awe in the realization that we exist at all in a universe so vast and indifferent. Dark energy will carry the galaxies beyond our reach. It will thin the cosmic web and darken the sky. It will write the final chapter of the universe in cold and silence. But it cannot erase what we have seen. It cannot undo the fact that for a brief moment, in a small corner of an expanding cosmos, matter organized itself into minds that could look outward and ask why. The universe is forgetting its history, but we have remembered it. And that, perhaps, is enough.